Hello everyone. We came up with some ID versus VGS simulations. We did the drain current versus gate voltage simulations at a constant voltage of VDS. And these were the curves that we achieved for 1.2 micron device and for 0.25 micron device. Okay. And the observations that you see over here is, if you see this particular curve, this is completely quadratic. Your drain current has got a quadratic dependency on your gate voltage, and that was pretty much clear from the model that we derived. For the drain current, we derived a model which was proportional to VGS minus VT the whole square in the saturation region. So this trend pretty much matches that one, but this one doesn't, because if you see for lower values of VGS, the trend is still okay. It still matches what we derived in as a drain current model for the saturation region. But for higher voltages of gate, the trend just doesn't match it. If you see, this line is much more linear compared to this one. So this portion of your curve is linear, whereas this portion of your curve is quadratic. So it says that your drain current is a function of the gate voltage, is a quadratic function of the gate voltage for lower values of VGS, and it's a linear function of your gate voltage for higher values of gate voltage. So that's the trend, and we need to come up with some model for this trend as well. And this is a very important effect that we see for lower nodes for 0.25 micron and below. For short channel, these are called short channel effects. One of the effects of short channel is velocity saturation, and there are even other effects which I will be introducing in a separate video, semiconductor device physics. In that videos we'll be explaining more about short channel effects, but in this case, one of the effects for short channel is the velocity saturation. Okay, so let's enter into the velocity saturation mode. This eventually we'll find out that this becomes one of the regions of operation. So initially you had three regions of operation. One is cutoff, linear, and saturation. For lower nodes, you will be having four regions of operation: cutoff, saturation, linear, and velocity saturation. Okay, so let's get into the concept of velocity saturation first. So the concept of velocity saturation says that for lower values of electric field, okay, for lower values of electric field, your velocity tends to be a linear function of the electric field, but after a certain point, after some cutoff, the velocity just saturates. Okay, it's as good as you're running at a speed. Your speed increases when with time, but after a certain point of time, your speed just becomes constant. It's as simple as that. It's an upper limit for the speed. Okay, so this is the trend. So let's take some few trends from directly from device physics lectures. We will talk more about the physics of velocity saturation and the reason for it in the in the device physics lectures. But in this case, let's see the trend. The trend is at lower fields, the velocity tends to be a linear function. Okay, but at higher fields, the velocity tends to become constant. Okay, and there are some reasons. The scattering effects is one of the reason. I'll come to that in a separate section. So this is the trend. Let's take it as it is from the device physics course. So right now, with this particular trend, we need to derive certain equations, because this velocity equation, which is mobility multiplied by electric field, this was used for deriving the model for drain current. Okay, so now we have to come up with some model with that will account for the velocity as well. Okay, so let's try to look into the derivation part of it. It's pretty simple. The velocity, let's put what we talked over here in some equations. So your velocity is a linear function for electric field which is less than the critical electric field. We have put a EC which says that it's a critical electric field. Okay, and your velocity becomes constant after a point where your electric field crosses the critical electric field. Okay, so there is a boundary over here. So let's try to derive something at the boundary, and then that can be used whenever we go for lower electric fields and for higher electric fields. We can actually use that boundary equations. So let's try to do that. So these are some equations that is being derived from device physics. So I'll not get into the derivation of this particular equation, but just take it from me for in this case, that this is the formula for your velocity at lower electric fields, and let's call it as VSAT, the velocity saturation, or the saturated velocity for electric field greater than critical electric field. Okay, let's take these equations and move further. So at E equal to EC, at the critical electric field, we can just equate this one by this one. We can take this, we can equate both of them and put E equal to EC, because let's try to derive something at the boundary, and we'll come up with some models for drain current as well. Okay, so let's equate this this at the boundary, and for continuity we'll put, which is basically the continuity point, we'll put E equal to EC, and that brings us to this equation. Your critical electric field is 2 velocity sat divided by mu n. So you equate this to this, you put E equal to EC, so this vanishes, 1 plus 1 becomes 2, and E is EC, so mu n EC by 2 is V set. So after juggling around the variables over here, you will get to this point where EC is 2 V set slash mu n. Okay, so now since we have this, we will go back, we'll rederive our drain current model. So sometime back we had these equations where your charge was a function of oxide capacitance and VGS minus Vx by Vt, and we had integrated this one. Okay, and your Vn of x was mobility into electric field. So we had used these two equations and came up with the drain current equation. So let's try to rederive the same drain current in the presence of your VSAT and the presence of electric field. So it comes to something like this. Okay, we'll use this boundary condition and try to derive the drain current, and the drain current comes to a very complex equation. It comes to something like this, which is not a very good model. It's a bit complex model for doing some hand calculations, and it's also very difficult to remember. Okay, so this becomes a too complex one to handle, because once we solve some more complex equations, it will become very difficult to manage this kind of equation. So let's try to simplify this one. So with that said, we'll come up with some simple model. We'll come up with one single model to do all these things. Okay, so before that, now since we know there is a region of operation at higher voltages of VGS, and that's called as velocity saturation. So we'll try to differentiate two different operating modes. One operating mode will be for long channel, which is greater than 250 nanometers, and one operating mode for short channel, which is less than 250 nanometers. Okay, so cutoff remains same, resistive remains same, the saturation remains same for lower voltages of VGS, and for higher voltages of VGS for short channel you will have another region of operation, which is velocity saturation. Okay, and also let's call VGS minus VT as VGT. So because the model that I will be showing you over here, that requires a lot of VGS minus VT, so let's call it, to simplify it even more, let's call it VGS minus VT, and let's call VGS minus VT as VGT. Okay, so wherever you see VGT in the upcoming equations, those will be all VGS minus VT. Okay, so with that said, let's try to cover the complete models over here. So your drain current is equal to 0 for VGT less than 0. Basically it's a state where your gate voltage is less than threshold voltage. Okay, so for VGS less than VT, it's in cutoff mode, and drain current remains 0 for both the cases. And for all other modes, we'll use a different model over here. So we'll use something like this. This model is called as ID is equal to Kn VGT dot mean, VGT multiplied by Vmin minus Vmin square by 2, and into 1 plus lambda VDS, because this is the one we would be needing for a saturation operation. Okay, so let's stay with this particular model, and we will identify what Vmin is. So Vmin will be the value which is minimum of VGT, VDS, and VDSat. For example, let's take this example. Let's say your VGT was minimum. You just substitute VGT to Vmin. You substitute VGT to Vmin, and then you come up with the drain current equation that will correspond to your saturation region. So what we'll do is, since I need some more time to discuss this particular model and what happens when Vmin is applied, when minimum of VGT, VDS, and VDSat is applied in this particular equation. So we need some more time to discuss this particular model. So let's try to substitute one by one in this particular equation, and let's try to come up with this simple model in the next video. Thank you.